Hey, Professor, we can't hear anything.
Okay. Can you hear me now?
Yep, loud and clear.
Okay, great. Yeah, sorry about that. So I'm just writing down the truth table of or, and okay, this is true if either one of those is true or both, and false only if both of them are false. And so the remark is that this is distinct from exclusive or, which is closer to the way we use or in English. So exclusive or is, I guess, another logical operation called, which is denoted with this plus with a circle around it. So exclusive or, we won't be using it too much in this course, but this is another logical operation. This is true if exactly one of P or Q is true and false otherwise. So this distinction is important. This is different from the way we use this in English. Okay. Any questions about this? Okay. So now we get to something which is actually a little bit more interesting, which is a conditional. This is so what's the definition? How do I want to say this? Yes. So the conditional P implies Q is the proposition if P then Q. And there are many different ways of writing this. So I'll write a few of them. So you can also say P implies Q. Or
Professor, would it be possible for you to go back, please? There are a lot of people in chat didn't catch the last page.
Okay. Yeah. Is there any question about the last page?
Professor, could you make a truth table for this too?
For XOR? Sure. So here you have TT, TF, FT, F. And so this is false here, true here, false here. So you can see that this is a different truth table. So this is a different logical operation. I mean, you can think of these as functions, right? They take the truth values of P and Q and spit out a new truth value. That's kind of what the truth table is specifying. Any other questions about this?
Yes, I have a question. So for the three main operators, they were negation, conjunction, and disjunction. And then this one is the exclusive or is the fourth one that we won't be using all that much. Is that correct?
Yeah, I mean, the classification main is kind of very subjective. This is a perfectly valid logical operation as well, but we won't be using it. Yeah.
And this is a non-major operator. So
I mean, it's also very important. I mean, computer science is extremely important. So
of course,
yeah, it's in the eye of the beholder. But yeah. Okay, so the conditional is if P then Q, P implies Q, Q whenever P. P is sufficient for Q. So it may not even be completely obvious to you that all of these English statements are the same. So again, to be completely unambiguous, let me just write down its truth table. So P, Q, P implies Q. So given the truth values of P and Q, oh, sorry, let's be systematic here. The truth table of P implies Q is this. And this might seem a little weird to you at first, because implies, or if P then Q in English, we usually use this to mean causality, right? Like, you know, like it usually refers to some kind of temporal or physical causality in the world. And the way we use it in logic, the metaphor, it's sort of intuitive metaphor for understanding what this means, is that P implies U is a contract. Okay, so P implies Q is true if the following contract holds. The contract is, if P is true, then Q must be true. Okay. Now, you know, in a legal contract or in some other contract, there are some conditions, right? And if you don't satisfy the conditions, the contract is void and it doesn't mean anything, right? And that's why the contract metaphor is useful here, because in particular, if P is false, if P is false, then Q can be anything. Okay, so if P is false, then Q is allowed to be whatever, but if P is true, then Q must be true. That's what the conditional means. And often, you know, a P in this context is called the hypothesis, and Q is called the conclusion. Okay, so it's different from a causal relationship. It's maybe best thought of as a contract. So in particular, if the hypothesis is false, then the contract always holds, right? Because the contract is always void. It doesn't, you know, it doesn't imply anything. And so this is very important for proofs and will come up a lot in the course. And to demonstrate this difference, let me show you a couple of examples. So here's a statement. If 2 plus 2 equals 4, then 1 plus 1 equals 2. Okay. So here's a proposition. It's a conditional, right? It's an implication that the first statement, P, implies the second statement, Q. Now, P is true, and Q is also true. Is the conditional true?
Yes.
Yes, because the contract holds, right? The hypothesis is true, and the conclusion is also true. So this is true. But now let's look at a different statement. So let's say if 2 plus 2 equals 4, then pigs can fly. This is false, right? Because the hypothesis is true, but the conclusion is false. This conditional proposition is false. And maybe more interestingly, let's look at another proposition.
Wait, I have a question.
Yep.
How come, like, how would 2 + 2 = 4 imply that 1 + 1 = 2? Like, isn't it like unrelated?
Yeah, so that's exactly the point here, that that we're not asking for a causal relationship between the first statement and the second statement. We're not asking how to derive the first and the second. We're asking, does this contract hold? That whenever the first one is true, the second one is true. Well, in this case, it does. Yeah, that's a great question. And now, you know, the flip side is, let's look at this statement. If pigs can fly, then unicorns exist. So individually, okay, this statement is false. This statement, as far as I know, is also false for some definition of unicorn. Is this conditional statement true or false?
True.
True, exactly, because the hypothesis is false. So this is true. Okay, so this is maybe the new thing that you're not used to. And now, so yeah, any more questions about the conditional before I explain some more sort of cool properties that it has that we'll be using a lot? You can just ask, just unmute and ask.
I was having some Wi-Fi trouble during that section. Could you do a brief overview? I think I have the idea, but just want to double check.
I don't really have time to do an overview. You can just watch the recording maybe.
Okay, thank you.
Professor, could you do the third example?
Sure, I can do a third example. Let's see. Do you want like a more mathematical example? So.
Oh, I just want one with like P being false.
Oh, I see. Yeah, I see. You want, yeah, sure. If pigs can fly, then 2 + 2 = 4. So is that conditional, true or false?
It's true.
It's true. Yeah, because the hypothesis is false, and then all bets are off. Right, so this is true. So these are illustrations of the entire truth table. The only way a conditional is false is if the hypothesis is true, but the conclusion is false. So that's the conditional. And the conditional is very useful and the source of much confusion. Here are some related operators. There are 3 that are important. So one is called the biconditional. This is denoted by a double arrow. And this is the proposition that P if and only if Q. And what that means is that P and Q have the same truth value. So this is a two-way implication. So this two-way arrow suggests that this has something to do with the single arrow, and we'll show in a moment that this is equivalent to P implies Q and Q implies P. Okay, so I've done something new here, by the way. I've combined different conditionals, right? But why not? The conditional is itself a proposition, right? And given any two propositions, I can combine them using an and, right? Using a conjunction to get another proposition. So I can actually keep repeating this process and get all kinds of new propositions. So what's the remark here? You can combine propositions repeatedly, right? You can apply these operations one after another, just like in arithmetic. You can multiply and then divide and then add and so on, as long as you make it clear what order you're doing it in using parentheses. So you need to use parentheses to clarify order. Right, so I've given you a bunch of operations and they apply to any proposition. So you can apply them one after another to get interesting ones that look like this. And we'll say why it's equivalent in a moment and even what equivalent means. So that's the biconditional. That's not the same thing as the conditional. So yeah, maybe I'll say in a moment what I even mean by that. Another interesting one is the converse. So the converse of P implies Q is Q implies P. Okay, so this is now, you know, taking converse is not itself a logical operation of you know, an arbitrary proposition. It's an operation that you apply to an implication and you just reverse the implication. That's called the converse. So for example, let's write one implication. So if you get 100 in this class, you will get an A, or I guess you get an A. Or I mean, okay, let's make it even more declarative. If you got 100 in this class, you got an A. Okay, so each of these is in the context of this class is a proposition. It's either true or false. You either did or didn't get 100 or did or didn't get an A. And this contract actually will hold in this class. So this is in this case P, and this is Q. And the converse is if you got an A, then you got 100. So this is Q implies P. And not both of these things are true, right, in the context of this class. Right, that it could be that you got an A, but you didn't get 100. So this is true and this is false. I mean, there's some background assumption here about the relationship between 100 and an A, but in the context of these class, the truth values of these statements are actually related this way. So the important sort of warning here is that P implies Q is not the same as Q implies P. Okay, and then the third one finally is, which is the most interesting and used a lot in this course, is the contrapositive. So the contrapositive of P implies Q is not Q implies not P. Okay, so you negate both the statements and then flip the arrow. So for example, in the context of the previous example, here's one statement. If you got 100, you got an A. And what's the contrapositive of this? Well, you have to negate the statements and flip them. So it says if you didn't get an A, you didn't get 100. So the first statement is true. Does the second statement sound true as well?
Yeah.
Yes.
Okay. So how do we really know this, right? So let's check this by showing that these two things have the same truth table. Okay, so here's an important fact. P implies Q and not Q implies not P are logically equivalent. And what that means is they have the same truth table regardless of what the truth values of P and Q are. Or I guess that's included in the definition of truth table. So let's check that. Let's just work it out here. P, Q, and let's just make columns for not P and not Q. Okay, so P, Q, not P, not Q. P implies Q, not Q implies not P. Okay, true, 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 false, false, true, false, false. So not P, you just flip everything. Not Q, you just flip everything. And now P implies Q, yeah, true, false, true, true. Not Q implies not P, so it's true in both the false cases. It's only false here, and it's true here. And then these two, you can see, are the same. Okay, so this is a linguistic manipulation that you can always do that preserves truth. And this is maybe something you've been doing your whole life, but it's actually very important to become aware of it when you're writing proofs, because it often actually changes the nature of a statement in a way which makes it, easier to prove or more clearly true. So this is sort of an important one, the contrapositive. And this device will be useful in many situations. So that's actually, so propositional logic is not a complicated thing. It's basically this little mini language that deals with propositions and these operations on them. And the whole content of it is, it tells us how the truth values of compound propositions are related to the truth values of their constituents. Okay, so maybe I'll just spell that out. Definition: a compound proposition consists of operations, logical operations or operators applied to propositions or propositional variables. This is just a piece of terminology. All the things we've been seeing so far are compound propositions. And the key point is the truth value of a compound proposition can be mechanically determined given the truth values of its constituents, right? Or given So what we're going to do now is we're going to study when can you tell if two compound propositions are logically equivalent. So logically equivalent means they have the same truth table. So
Professor, I'm sorry to interrupt. What's that word after it comes? What's that word after it?
Its truth value.
It's no. After right after values of its
constituents.
Constituents, yeah.
Oh, constituent. Thank you so much.
Yeah. Okay. So true. Okay. So two compound propositions are logically equivalent if they have the same truth table which is the same thing as saying they have the same truth value for all, regardless of what the constituents are. Okay, so two compound propositions are equivalent if they always have the same truth value. Regardless of the truth values of the propositional variables. So one example of an equivalence is the compound proposition P implies Q is equivalent to the proposition not P or Q. So this notation means equivalent to. So since I'm running out of time, I won't do this now, but you can check this using just by checking the truth tables, right? So you can check using truth tables. And okay, within this so let's see, what do I want to say about this? Yeah, so they're essentially well, oh, sorry, somebody raised their hand.
For the not P or Q, is that a negation of P or Q or a negation of P?
Okay, that's a good point. So yeah, so this is a negation of P, and okay. So if I wanted to be completely explicit, I should have put parentheses. But just like in arithmetic, there is a sort of precedence order in these logical operations. And the main thing you need to know about it is that not always takes the highest precedence. So it's a great question. So remark.
Thank you.
Not always takes highest precedence. Okay. So, okay, actually what I've decided is, since there are only 5 minutes left, rather than build up more theory of this equivalence, what I'll do is I'll do a fun example showing that the stuff we've learned so far can actually be used to do something non-obvious. So okay, we'll finish this section next time. Instead, what I'll do is I'll do a little puzzle, which is sometimes called knights and knaves. Okay, so there are two kinds of people in the world. Let's say knights, and knights always tell the truth, and knaves who always lie. Let's say this is so this is a ground truth, okay? So there are these two kinds of people in the world. And you have these two people, Alice and Bob. And they say the following. Alice says, Bob is a knight. And Bob says, the two of us are opposites. So one of us is a knight and the other one is a knave. So the question is, can you figure out who's a knight and who's a knave? Okay, so this is a standard riddle. And if you just tell this to someone, it's not, at least to me, it's not intuitively obvious what the answer is. So what we're going to do is we're going to encode this in propositional logic and then easily find the solution. So the whole point of propositional logic is to mechanize this process of deductive reasoning. So let's encode this in propositional logic. So let's make two propositions. P is the proposition that Alice is a knight. Not P is the proposition that Alice is a knave. Q is the proposition that Bob is a knight. And not Q is the same thing, except Bob is a knave. So these are, they're propositions. They're either true or false. We don't know yet which one, but it's one or the other, right? Because there are only two kinds of people. And now let's write down what we know about the situation in the language of propositional logic. Okay. So, what information do we have? Well, we have these four pieces of information, right? 1, 2, 3, and 4. And let's write them in the language of logic. So Alice said Bob is a knight. Okay. Now our propositions only concern whether or not Alice and Bob are knights or a knight or a knave. So what do we know about knights? Well, knights always tell the truth, right? And these always lie. So one way to encode this statement when combined with item 1 is that P is true if and only if what Alice said is true, right? And what Alice said is that Bob is a knight, and Bob is a knight is a statement Q. So, if we were to write down what we learned from this information in propositional logic, you get that P if and only if Q, right? Because, well, Alice is a knight if and only if Bob is a knight, right? If Alice is a knave, then Alice is lying, and then Bob is also a knave. Similarly, if Bob is a knight, then this implies that what Bob is saying is true. And what Bob is saying is that the two of us are opposites, and you can write that in propositional logic as P and not Q, or not P and Q. And actually this implication goes the other way, because remember, if Bob is a knave, then what Bob is saying is false. So what came out of Bob's mouth, which is the statement, is false if Bob is a knave, so this actually goes in the other direction. I'm going a little fast, I guess, because I ran out of time. But a good exercise is to just write the truth tables. Whenever in doubt, just write the truth tables. So you can check this using truth tables. And now we have these two statements. So we've described this riddle in terms of propositional logic. Okay. Oh, and please bear with me. I know we're on time, but maybe just give me one more minute since we missed some time because of that, the technical issues. But now what I'm going to do is I'm going to use this sort of precise description to actually figure out the values of P and Q. I can now treat these almost as if they were equations and try to solve them for P and Q, right? So let's try to solve these. So the way I'm going to solve it is, well, there are only two possible answers for what P is, right? It's either true or false. So let's just check each one. So case 1 is that P is true. Well, in this case, from the first equation, I get that true if and only if Q. So that implies that Q is true as well, right? But now from the second equation, I get that I now have true if and only if this P and not Q, or not P and Q. But now let me just plug in what P and Q are. P and Q are both true. This is true if and only if I have true and false, or false and true. This is true if and only if false, and this is false. Right? So I've reached a contradiction from this assumption that P is true. It's a bit like it's sort of like algebra. I just plugged in P into these equations and then just applied the definitions of these logical operators to reach a statement that's clearly false. So therefore, P. So what's the conclusion? The conclusion is that P is false. Why? Well, P is a proposition. It has to be true or false, right? There's only two options. If it's not true, it's false. So, okay. And then again, from the first equation, Q is also false by P if and only if Q. Therefore, both are names. Okay. So this is sort of a mini demonstration of really what mathematics is all about. It's about making these tiny obvious steps to reach a non-obvious conclusion. And the point is, if you're really precise, and this is why I use the word mechanical, if you don't lose anything along the way, you can chain together all these tiny observations to reach some non-obvious observation like this one. Anyway, thanks for bearing with me, and we'll continue next time.
Thank you, Professor.
Thank you.
Thank you. Have a good night.
You too.
Have a great evening.
Thank you.